So before we do examples, I know I promised you that in the last video, but I kind of lied to you. I at least want to talk about one other topic before we start doing some of these examples because it is related and it's something that could play a factor in some of the questions that we're going to see. Notice that up until this point, we've talked about carbon bonded to a carbon, double bonded to a carbon, and carbon triple bonded to a carbon. And of course, they all have to have 4 bonds, so we go through and we satisfy those 4 by adding hydrogens on. And this is what we did in the previous videos, and this is how we described sp3, which were single bonds, sp2s, which were double bonds, and sps, which were triple bonds. What I want to do in this video, though, is to bring in this definition of an ion one more time. It's something that's always haunted us throughout this lecture series, right? This ion, if it creates a charge, can do funny things with electron configurations and Lewis dot structures and everything else, and hybridization theory is no different. So I want to do at least 1 or 2 examples of what a charged species would look like and how to handle those, just so that we will know this going into some of those problem sets that we'll start doing in upcoming videos. So if I take something like CH3 with a positive charge, how do we handle something like this? Well, just like in all of the other examples, the electron configuration of that carbon is 1s2, 2s2, 2p2, right? So in the first block, there we go. In the second block, there we go. And in the third block, we have 2 of those electrons. And just like always, we promote this electron and we put it into an empty p orbit. So this gives us 4 available bonds that carbon can choose. Well, he does have 4. He's got 1 to that hydrogen, 1 to that hydrogen, 1 to that hydrogen, and then this weird kind of positive charge that goes on. So how do we handle this? Do we really count that as a bond? Do we really count that as a 4th? Yes or no? That's the question that we have to answer. So we at least know that there are 3 lines to 3 atoms. So those 3, we automatically know that 3 orbits have to be used. So at the minimal, this is going to be an S and a P2 hybrid. It has to be, okay? There's no other choice below that. The question that we have, though, is this positive charge. What does this positive charge actually mean? Does that represent a bond? And if so, then we include this 4th p orbit. If it does not represent a bond, then it will not include that p, and we will have a different hybrid. Okay, so here's the reasoning. This positive charge means no electrons, right? This positive charge means that it has lost electrons from its normal state. That does not represent a bond. This bond represents 2 electrons. This bond represents 2 electrons. This bond represents 2 electrons going to those 3 atoms. It does not represent bonding. Therefore, we do not need that other p orbit that is out there. That also means that this positive CH3 group is sp2 hybridized. There's nothing here. There's no bond to another atom. Therefore, we do not need this last empty orbit, and we only need the first 3 for bonding. So therefore, we call it an sp2. Okay? We also have a proper name for this. Again, it's very common in organic chemistry. This is going to be called the methyl cation. And of course, methyl is the name that's given to a 1-carbon chain. You'll learn that a little bit later. And cation represents the positive charge. So the methyl cation. Now, let's take it another step. Let's say that this time we have CH3 with a dot. What do we do in this case? This is what we would call a radical. And a radical is anything in chemistry that has 1 electron that's unpaired. Because these things go crazy. And they can do things that we don't want them to do. They're radical. They're out of the box. So how do we handle something like this? Well, I'm going to give you the same description. 1s2, 2s2. The P has 3 degenerates, 1, 2, 3. And in order to get that, we have to erase that bond there. So we promote that electron just like always. Now the question is very similar. We have this carbon. It has 3 atoms that are attached to it. And then it has this one little funny electron that's also sticking there as well. All this time, we have talked about the same reference points. How many atoms are they bonded to? And in this case, there's at least 3. So once again, it's going to include the S, and it's going to include at least the 2 P's, at least. So at bare minimum, this is going to be an sp2. The question now is, do we count this last orbit as part of the hybridization? And whenever you have 1 electron, this bond, how many did it represent? That's right, 2. This one, 2. This one, 2. This free dot, there's just 1. It's not truly a full bond at this point. So we do not include that as well. And this is proper sp2. I know that we have a orbit, and this is a p lobe, and that has 1 electron that is unpaired, but that is not a full bond at this point. So a methyl radical is sp2 hybridized, and a methyl cation is sp2 hybridized. The carbon that's involved in those structures are both sp2 hybridized for that reason. Now let's take a look at the CH3 with 2 electrons. We're going to call this the methyl anion. And the reason is because it carries a negative charge. This is not the formal charge for carbon. It's got 3 bonds plus 2 more dots. That's a total of 5. 4 valence minus 5 is a negative 1. That is why that carries a negative 1 charge. This methyl anion, does it behave the same way? Well, 1s2, 2s2, and then here's the 3 degenerates. There's 1 and there's 2. Just like before, we promote. We get rid of that electron and we push it up. When we do that, we open the site for 4 bonds to carbon if needed. This carbon has 3 bonds for sure to those hydrogens, just like in all the other cases. But now this time, we have 2 dots that are on that carbon. The question once again, do we count it? Yes or no? Well, if I look, there's 3 atoms that are attached to that. So I know at least it has to be an sp2 because we need 3 in order to get that structure there. Now the issue is, what do we do with this p lobe that has this time 2 electrons that are present? In my previous description, pay attention to what I did. I circled this bond and I said that represents 2, that represents 2, that represents 2 electrons. Guess what, folks? This time we do have 2 electrons. It's right there. So we treat this as a possible bond. If something comes into the vicinity and it needs that bond, this carbon is very open to that bond taking place because it has everything that it needs for the bond. It just needs the atom. So because those 2 electrons are present, because it's a pair, because it's taking place in the p lobe, we treat that as the 4th bond. So that means that we do go back and we do include this 3rd p degenerate, and we call this an sp3 because we have used all of the hybridization possible to carbon. So methyl anions are going to be negative in characteristic, and they are going to be sp3s. Okay, so that's the story with methyl anions, methyl radicals, and methyl cations. So now that we see how charges are going to start playing an effect on hybridization theory, we can now get turned loose on some examples that we might see from the textbook.